So welcome back, and I hope you managed to do the exercise for me. In this video we're going to look at the answer to the exercise and then consider how we might find out if we can actually make MU. So let's have a look at one answer to the exercise. This is just one way of doing it. Your way of doing it may be different, and if it accords to the rules, then it's just as valid as my way of doing it. So I started by using the doubling rule. So I transformed mi into m ii. Then I used it again to make m with 4 i's. Then I turned the first 3 i's in that string into u. And then I doubled that again to get mui ui. Then finally I added a u to it to get m ui ui u. And there are other ways of doing it. The question is though, can we derive mu? So I've got quite a collection of statements here, all of which are true. mi, m-double-I, m-4-i's, miu, mui-ui, m-ui-ui-u. But I want to make mu. That's my goal. Can I do it? Well, typically when I'm faced with a problem such as this, I think to myself, well, maybe I could write a program to do it for us, because I'm a very lazy person at heart. And I'd rather get the machines to do it. They're very good at this sort of thing. Computers are not only good at adding up, they're very good at manipulating symbols very, very, very quickly. So what I could do is I could write what's known as a search algorithm. It's a program that searches. So what I'd do is I'd start by getting it to store a list of all the theorems it's made, and then I'd pick one of those theorems and I'd see what new theorems I could make by applying the rules. So at the moment I've only got mi. So first of all I'll pick that and I'll see what theorems I can make from mi. So have a think for the moment and think about what theorems can you make from mi. So the answer is you can make m with 2 i's with the doubling rule, or you can add a u. And the way that we write it is like this. Now this structure that I'm drawing here is known in computer science as a tree. And it's one of the data structures that's very useful to us. Certainly in storing data and in searching data, we're often working with trees. Sometimes they're called binary trees because there's only a branch of 2 new ones. But this tree is not going to be a binary tree. It's going to be a tree where there are a lot of possible branches coming out of each one. And we'll see that in a minute. So what I now do, okay, so I've now got 3 true theorems, mi, m-double-I, miu. Now the top one here, it's already been what's called expanded. I've expanded it out to give these, but these haven't been explored yet. And these are going to lead possibly to new theorems as well. So I now need to pick one of these 2 and expand it. So the one that I've expanded is this one. And expanding means I see what new theorems I can make from it. Well, this isn't a very interesting theorem because the only new theorem that I can make from it is the one that you can get by using the doubling rule. You can always use the doubling rule because there's always something to double. So whatever comes after the m, you can double it. But that's all you can do here. It doesn't end in an I, so you can't use rule 1. Doesn't contain 3 i's, so I can't use rule 3, and it doesn't contain 2 u's, so I can't use rule 4. So it's not that interesting. Let's go to this theorem instead. So now I can look at this and I can say, where can I go from here? What can I do after m with 2 i's? Well, it ends in an I, so I can add a u, and I can also always apply the doubling rule. So there we go. I can add my u, or I can double. So now I've got 6 theorems in my tree, and these 3 here are still unexplored. I still haven't looked to see what rules I might apply. So let's pick one of these, and we can pick any of them. So I think I'll pick this one here. Well, it's one of these not very interesting ones. The only thing I can do is to apply the doubling rule. So there it is. A clever search algorithm, one that's got its, might say, okay, I reckon this might be a good one to explore next. So it can pick which one it would like to explore next. So it picks this one next, say, and that's an amazing one because you can add a u to it, giving m 4 eyes and a u. You can double it, which gives m with 8 eyes. And you can consider where this amazing string would go next. Or you can turn 3 eyes into a u here. So those first 3 eyes, they can turn into a u. Or the last 3 eyes, they can turn into a u. So all of these are new theorems derived from m with 4 eyes. And you can then keep searching. You might pick this one next to expand. You can add a u to it, or you can double it. And you could keep searching like this. So my program, once I set it running, it could search all day for me. Just keep going, search, 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 search. But the question is, would it ever get to mu? You might like to consider that. If you're already a good programmer, then you might like to write this search algorithm for me. I'll be showing it to you in Python later on in the week because I've actually written it myself, and I'll show you it running. But for the moment, just consider the question, will mu ever crop up in my tree here? Is there something about the form of these strings that means mu will crop up? Or is there something about the form of them that means it won't crop up ever? So once we've been looking at this system and staring at these strings for a little while, we start observing a few things about it. What we do know is that all theorems start with an m. You'll notice that straight away. And you'll realise from the form of the rules why that has to be true. And the rest is a mixture of u's and i's. There's never any other letters in there. You just can't make them. So we can write that as what's called a regular expression. That's what this thing is here. This mu star I star all star. That means that it's an m followed by 0 or more u's, followed by 0 or more i's, and the whole thing repeated. Then that basically just says it's strings followed by some u's and some i's. We know that some strings are definitely not theorems. So IUM is not a theorem, doesn't start with an M. This one's got an M in the middle of it. This is a mixture of M's and U's and all kinds of M's. There's M's in the middle here, and you could never get an M in that position. What we also know, or I hope you work this out, is that there are infinitely many theorems in this system. So in other words, if you show me a theorem and say that's the longest theorem I know, I'll show you a longer one because all I need to do is to apply rule 2. That's the doubling rule. And as I've said already, the first 2 rules, they make longer strings, and the other 2 rules make shorter strings. So maybe to make mu, what you need to do is to make a very, 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 very long string and then use rules 3 and 4 to shorten it down. Certainly, just looking at our tree there, mu didn't appear quickly. But maybe if we take that branch there, this m with 8 eyes, and we keep exploring down here, maybe we'll make a very, very long string, which then becomes shorter again. That would be the hope. So, as I said, all theorems start with an m, and the rest is a mixture of u's and i's, and we write that as m u star I star all star as a regular expression. and the star means for 0 or more occurrences of it. Is this actually enough to characterize all the theorems of MIU? In other words, is that if I accord to that pattern, does that mean it's a theorem of MIU? Turns out, in fact, it's not. So that pattern there it's not good enough to characterize the theorems of MIU. So we're going to need to make the description of our theorems a bit more restrictive. And what we actually want is what's called a decision procedure. What this is, it's an algorithm. Procedure is the same term as algorithm. So it's a decision algorithm. You feed in a string and the decision algorithm will think about it and will eventually spit out the answer true if it's a theorem, or will spit out false if it's not a theorem. So that's what we've got to try to find. But the first thing to do is to explore the system. Decidable problems are a big thing in computer science. So if, say, you've got a question and the answer to that question is yes or no, it might be, is k a prime number? So for some k that I give you. So I say to you, is 91 a prime number? And you think about it for a little while, and eventually you say, no, 91 is not a prime number because I've worked out that it's 7 times 13, so that's not prime. If I say, is 97 a prime number? You run your little procedure in your head that checks for, see if it's a prime number, and eventually you say, yeah, it is a prime number. Well, they've got another problem here, which is, I'll give you a string. Is string S a theorem of the MIU system? So I want a program that is going to tell me whether or not the string is a theorem of MIU. If we have a procedure for all cases for our problem that can say yes or no in a finite amount of time, then that problem is called decidable. It's a decidable problem. The interesting thing in computer science is that some problems are undecidable. So if there is no procedure, we have an undecidable problem, and that corresponds to a non-computable function. So we better know about these problems which are undecidable, because if we try to write a computer program for them, we're going to fail. One of the things is that the program that I talked about that searches for the thing is not a decision procedure. Why? Well, let's say I set my program that searches, and as input I say, I'd like you to search for the string XYZ. Well, it's never going to reach the string XYZ, so it will just search forever and ever and ever, waiting for the string XYZ to come out, and it's never going to come out. And therefore, this program will never come up with an answer. It will just run forever. So that program that searches is not a decision procedure. We're going to need something better than that as the decision procedure for MIU. So the challenge, the overall challenge of the MIU problem, and I don't expect you to immediately get this because it's quite tricky. What I'd like you to do is to understand what we're trying to do. Can we come up with an algorithm? So this is like a mini challenge for us. Can we come up with an algorithm for strings which are theorems of MIU? Just trying to see if the string starts with an M and then consists of U's and I's, that's quite good. But the problem is that some strings seem to be very difficult to find. Try finding MUU, for example. Try finding M with 3 I's after it. You might find they're quite tricky. Is there any pattern to the theorems that my program might produce for me? Can I inspect the rules that I've got to find the reason for the pattern being there? So that's the challenge that we're going to try to face. But for the moment, what I'd like you to do is to consider the MIU system as a whole. And I've got a little quiz for you to do to show that you're understanding what's going on with MIU and that you truly understand it. And then later in the week, we're going to start thinking about what algorithms actually are, and we'll start trying to think about what this decision procedure is. See you soon.